All right, so this is section 10.2, day 2, video 2. So the first section, the first video we talked about arc length and how to find the arc length in parametrics. Um, in this one, we're going to introduce motion along a curve. Specifically, we're going to talk about, it only says velocity and acceleration vectors, but we're also going to talk about the position vector. um, You'll get much more on vectors in Calc 3 because pretty much that's what is talked about in Calc 3 is vector calculus. But we'll introduce the general idea here in this video. Vectors are not terribly difficult. Um, Basically, the idea is that every point in space, um, well, that's probably a bad way to start it, but you can get to any point in space by creating a vector from another point in space. Basically, if you had something like this point here and I want to get to this point, I can create a vector that starts at one point and ends at one point. Basically, it's like a line segment that goes from one point to another. But the important part is that the line segment has a specific direction attached to it, as well as a specific magnitude or length of that vector. um, so typically what we call the position vector in calculus is r of t. Usually it's not a capital R, it's r of t, like this. The little notation on the top is um, basically it looks kind of like a ray, but it's only supposed to have a top piece to it. Like that's your vector notation. It's just kind of hard to see, and I think we may have actually used the wrong notation there, but it's typically r of t, representing your position vector, and this notation, this is all bad, so let me kind of rewrite some of this. This would typically look like this, r of t, and we usually use these kind of greater than, less than, or angled arrow brackets, or whatever you want to call them, x, y, and that would be a vector going from a specific x and a y value. It can be written, especially in things like physics and other notations like that, as I and j after the x and y. I will not typically use that notation in this particular course, but again, it will be used if you go into physics and or even Calc 3 will use it. So, oops, didn't actually mean to erase that. Let's just leave that there. That is the notation that we will use for a vector, letting you know that it's a vector. So the length or magnitude of a vector is going to basically be given in 2 dimensions as the square root of x squared plus y squared. If you think about that, that should make sense, because if you've got some kind of a vector, you can have an x component in this direction and a y component in that direction. So here's your x, here's your y. If you want to find the length of the vector, it's just going to be a Pythagorean theorem. X squared plus y squared equals the square root, x squared plus y squared equals the length of the vector squared. We can call it whatever you want to. We'll just call it v, I guess. And then you would take the square root of that part to get the length of the vector v. The angle that is created, there is an angle, and that angle is in here. We'll call that theta, and you're going to be able to find that by using the tangent of theta equaling y over x, which again should make sense from geometry, opposite over adjacent. And then you'll use an inverse tangent idea to be able to find the angle. Okay, that's how vectors, really basic introduction. A lot more that goes into that. Again, more to come on that at some other point in time. So just like in just like in Cartesian plane, you can find the velocity vector by taking the derivative of the position vector. And it's actually really simple. You're just going to take the derivative of the x portion and the derivative of the y portion, and that becomes your velocity vector. And this is horrible notation. I really need to just retype all this stuff. It should look like this. And then again, you can use the I and J, but again, I'm not going to do that. Speed. Speed doesn't have a direction associated with it. Velocity does, if you remember from basically Calc 1 or AB types, Calc AB stuff. Velocity can indicate something which in a positive direction or a negative direction. Doesn't mean that the velocity or the speed itself is positive or negative. It just means that the direction the particle or the whatever it is it's moving is moving in a specific direction. So velocity can have direction attached to it, which is why it can be positive or negative. Speed, however, cannot, which is why you see what looks to be like an absolute value around the velocity. And it does actually technically mean absolute value because what it really is talking about in vectors is magnitude. Okay, that is the symbol for a magnitude, the absolute value bar. And the way you find the magnitude or the speed, which is non-directional, so it's just always positive, is to take the square root of dx dt squared plus dy dt squared. Should look very similar to the arc length. As a matter of fact, basically that is one component of the arc length. And if you think about it, that is one extremely, extremely tiny line segment. So basically at a single point, you are finding the speed at a given moment in time. Then if you were to integrate that, you would get the length of the arc because you'd be taking that little line segment, adding them all up. So that's really what we're doing here. The acceleration vector is the derivative of the velocity vector. So basically you just take the derivative of each one of the components of the velocity vector, and again, poor notation, mostly just because of the angled brackets needing to be there. So that would be the acceleration vector. And that would tell you the acceleration at a given specific moment in time, or the vector that would lead to that. If you actually want to find the acceleration of the particle, which is the magnitude of the acceleration vector, it's the same exact principle. This is not something that I will actually use in any of the stuff that we are doing, but it is the magnitude, which is the square root of each one of the second derivatives squared added together. All right, these examples, these first few examples anyway, are not going to be exceptionally long until we get to, probably, well, I guess the third example starts to get long. So we'll probably only do the first, let's see, one, two, maybe we'll do the third example if we have time. We'll see. First two examples are short. All right, so if a position vector of a particle moving along a curve is defined by, now they called it S of t, R of t, either one of those is fine. Just know that they're kind of interchangeable. S is typically your position in Cartesian. R of t is typically your position vector in parametric. Doesn't really matter. And again, those should be angled brackets. This is horrible. I really need to change these at some point. Then the velocity vector of the particle at time t equals 0 is what? So if we want to find the velocity vector given the position vector, we simply take the derivative. So the velocity vector is the derivative of the position vector, which is the derivative of the first component, derivative of e to the negative t, bit of a chain rule, it's just going to be negative e to the negative t. And then the derivative of negative sine of t is the second component, which is going to be negative cosine of t. That's your velocity vector. If we want to find the velocity vector of the particle at time t equals 0, we just plug in 0. So the velocity vector at time t equals 0 is negative e to the 0, which is negative 1. And then negative cosine of 0. Cosine of 0 is also 1, so that would also be negative 1. And that is your velocity vector at time t equals 0. Okay, not difficult. Okay. Example number 6. A particle moves along a curve. So the x of t is 6t squared plus ln of t, and dy dt is sine of t plus 2. What is the speed of the particle when t equals 2? So now we're looking for speed. In order to find speed, it might help to find the velocity vector, but you don't have to. What you need is you need the derivatives. So let's write those down. So we're going to need, oops, sorry, we're given the derivatives. You basically just need to, no, we are not given the derivatives. I apologize. We are given x of t and we are given dy dt. We're given half of that. We need to find dx dt. So let's find dx dt. I'm getting ahead of myself. So that would be 12t plus 1 over t. Now I need to find the speed, which is going to be the square root of dx dt, so 12t plus 1 over t squared, plus dy dt, which is sine of t plus 2 squared. That's the equation for the speed. Now if I want to find that at t equals 2, we're simply going to plug in t equals 2 and figure out what the speed is. So we should get that the speed at t equals 2, plugging in a 2 for all the t's, taking the square root, you should end up with about 24.672. Again, assuming you plug in 2 correctly into your calculator, plug all that stuff in, that's what you should get for the speed. All right, I am debating, but I think we're going to cut this one off right here. We're going to do the last 3 examples all in one video. They are relatively long examples, so it'll probably be a 15 to 20 minute video. So we'll stop this one here and come back with a third one.